Yeah. All right. How's everybody doing? We're here, so I'll take that as a positive sign. Poor Andrew is like all alone in Williston. Usually there's kind of a crew here, but we're not sure what's going on there. We are Deep. So Deep is usually in the room, and he's attending from home, I guess. All right. So we are we had one example left, I think, on that last section. So we're gonna do that, and then we'll work on permutations and combinations. We're turning in that take-home test today, so I'll start by taking questions that you all might have.
Number 5.
Mm-hmm. Is there a specific question about number 5, or?
Yeah, I'm having a hard time with it. Just number 5 in general, I guess.
So 5 asks us to prove that 3 divides n if and only if three divides n squared. So I think I maybe posted an announcement that addresses some of this, how we're going to approach it, but the first thing is that this is an if and only if. So you have to write 2 proofs. You need to, in the first proof, say in this direction, you need to show that 3 divides n implies that 3 divides n squared. That one is pretty straightforward and direct. We did one really similar to that. Let me see if I can't find it.
It's that Wednesday one, right?
It's which one?
It's,
The March 19th?
yes.
Okay.
No, that's or can't be March 19th.
Oh. Oh, man. Wow. Okay. Yeah. Okay. Oh, I think it's Monday the 17th. All right. Oh, here we go. Example 2.1, we said, if n is even, then n squared is even. So I'm going to rewrite this in the notation that we see on the test. This is like saying, prove that if 2 divides n, then 2 divides n squared. So we're just doing that if 3 divides n, then 3 divides n squared. You can use this example kind of as a model for how to set up that direction, right? You suppose that 3 divides n, that means it's a multiple of 3. N is a multiple of 3, and then you show that n squared has to be a multiple of 3. And it's really just a few lines is all it should take. The other direction, in the other direction, you're going to show that 3 divides n squared implies that 3 divides n. And this is the one we have to do indirectly. We don't want to start out by supposing 3 divides n squared, because that doesn't really get us an expression for n without taking a square root, and then we don't even know if we're still talking about integers anymore. So I would do this one by using the contrapositive. So what you want to do is prove that if 3 does not divide n, then 3 does not divide n squared. And we did one similar to this. I think it was example 2.2. We showed that if n squared is even, then n is even. In other words, rewriting this in the notation of this problem on the test, we showed that 2 divides n squared implies that 2 divides n. We did this by contrapositive. We said, let's suppose n is not even, which means it's odd, and that meant we knew we could write it as 2k plus 1. There's only one case, right? If n is not even, we know that means we can write it as 2k plus 1. Things are a little bit different, only slightly, when we start out by supposing that 3 does not divide n, because there isn't just one case then. Right? Every third integer is a multiple of 3, and then there are 2 more after that are not multiples of 3. So if you're not a multiple of 3, that gives you 2 cases that are n is either 1 more than a multiple of 3, and in case 2, n could be 2 more than a multiple of 3. And what you want to do is take each of these cases, work them out, and deduce that n squared is not a multiple of 3. Does that help at all, or is there still? I don't know if you already saw the announcement, or maybe we talked about this before. Maybe I'm not answering a question that you have, but.
Sorry, barring any comments from the original asker, I've got one question about the end of this problem.
Yeah.
So, let's say you do your algebra there with what you just showed, and it boils down to where you can't get rid of that remainder.
Yeah.
Are you done at that point?
Yeah, basically you want to show if it's not divisible by 3, you'll be able to conclude that it's not divisible by 3 if you can show that n squared is 3 times some integer, either plus 1 or 3 times some integer plus 2.
Okay.
You want to show that it takes on one of those forms. And then you'll be able to say, oh, okay, then now I know n squared is not divisible by 3. And you want to do that for each of these. And it works kind of the same way. You're doing the same kind of algebra. You get a similar form.
Thank you.
Mm-hmm.
Rachel, would you prefer, let's say we boil it down to n squared equals 3 times some integer plus another number, even if it's not 1 and 2, as long as it's not a multiple of 3, we could deduce the same thing.
I mean, yeah, you can deduce the same thing. I would say that the argument is cleaner and kind of takes on a nicer form when you say, oh, I know. You could still write the argument, but I feel like it makes you have to do more explaining. I mean, it would still be valid. It would still be true. It's
10 or something. Obviously, you could split it up.
You could say, and 10 is not a multiple of 3, so I know this whole thing is not a multiple of 3. Yeah, that's valid. I would say that it's not as clean. Most people would, like math folks would just go ahead and segregate out the multiple of 3 so that you have the plus 1 or plus 2 at the end.
I hadn't thought about it.
I have a question.
Yes.
Problem, please.
Mm-hmm.
So I saw that it's if and only if
Mhm.
problem as well.
Okay. Yeah, so that is just how they define the relation. So there are not actually 2 parts to that proof. In number 3, they say that A, B is in the relation if and only if. That's a really good question. If f of A is equal to f of B. That's just our starting point. They give us that. Then we are not asked to show an if and only if. They're just saying this is what the relation means. That 2 things are related if f of A is equal to f of B, and also if f of A is equal to f of B, that means they're related. So they're just being really precise about how this relation is defined. So there's not a 2-direction proof to do here.
So just prove the equivalence
Mhm.
relation.
Yep, just show that it's reflexive, symmetric, and transitive.
Thank you.
I actually have one more question as well, Rachel.
Mm-hmm.
The very last problem, I just don't understand what that Z notation is.
Oh,
Subset.
yep. So Z7 is the same as Z mod 7Z, and it's the set of equivalence classes for the relation, being equivalent mod 7. So it's 0, 1, all the way up to 6.
And it's as simple as that. Okay,
Mm-hmm.
awesome. Thank
And
you.
you just want to make a multiplication table, and then don't forget to reduce those products, right? Like, you shouldn't, in your multiplication table, you should not have something that this is equal to, 15 mod, when I multiply 3 times 5, 3 times 5 is 15, but like that's not the final result that should go in that cell, right?
Right.
Okay.
Awesome. Thank you.
Mm-hmm. Other questions before we do more counting problems?
Yeah, how do we go about doing number 4?
Yeah, I think that might be one of the problems that. Oh wait, I did get a question. I think that was part of the announcement that I sent out like a few days ago. So number 4 says we have a function from A to B. And we want to show that B1 and B2 are subsets of B. Maybe they overlap, maybe they don't. I'm going to allow for that possibility. And we're looking at the preimage of the union. So that means the preimage is all the elements in A that map into that union. And we're asked to show that the preimage of B1 union B2 is equal to the preimage of B1 union with the preimage of B2. So if I pull each one of these sets back into A, like all the elements that map to B1, that's the preimage of B1. And here's all the elements that map to B2. That's the preimage of B2. What we're trying to show is that if I look at this as a whole, this union over here on the B side, and I pull it back, that's the same thing I'll get if I take the union of these two individual preimages in A. So we're trying to show that two sets are equal, so there are two proofs to write. In part 1, you're going to show that the preimage of B1 union B2 is contained in, is a subset of, the preimage of B1 union the preimage of B2. And the way we do a containment proof is we say, well, let's let, some element A be in the preimage of B1 union B2. There's not much we have to go on here, except we just know we have a function that goes from one set to the other. So I'm looking at something in A. If you have an element in A, the one thing we can do to it is apply F and send it into B. If we have an element in B, the one thing we can do to it is pull it back and see what mapped to it from A. That's really, we don't have a lot more. We don't have much else at our disposal. So that's what you want to play around with. And then you want to show that A is an element of the preimage of B1 union the preimage of B2. And, to be in the union, you only have to be in one or the other. So you just got to be able to conclude, I know it's in the preimage of B1 or it's in the preimage of B2. We have an element that we know maps into the union B1 union B2. And we want to show that it has to map into either B1 or B2. In part 2, in the other part, you just go the other way. We're going to show that the union of those preimages is a subset of the preimage of the union. And it goes the same way, right? We're going to let A be an element of preimage of B1 union preimage of B2. You're going to do some stuff with the function, right? If you have an element of A, really the only thing we can do to it is apply F and see where it sends us. And then you want to show that A is an element of the preimage of B1 union B2. And once you have both of those parts, you will have shown that these two sets have to be equal to each other.
re-enters, but like how are you handling redos for this test?
Oh, on the take-home test, you can pick one problem to rewrite. So when you pick that problem, like you get to pick it, right? When you pick that problem, what your goal is to maximize the points you get back, just consider the weight of the problem too. Okay, should we do some counting? Okay.
One more question about the redo part.
Yeah.
If you redo it and you do worse than you did before, it's going to count?
No, you cannot lose points.
Okay, just
Yeah,
make sure.
it's risk-free. Also, just want to make a quick announcement. I graded assignment 4, so that's up. Maybe you got the announcement that you have a new grade entered. And I am definitely behind on rewrites. So if you submitted a rewrite for assignment 3, or I think even assignment 2, I've got some rewrites those are coming. I always prioritize new assignments to get you feedback on that work that you did. And my goal, I hope, is to get those rewrites graded over the weekend. So let's.
Sorry.
What's that?
Because I handed in my exam early, can I do the rewrite for assignment 3?
Can you do the rewrite for assignment 3?
Yes, I haven't handed it yet. I know
Oh.
the due date was like Monday or something.
Yeah, I mean, I guess I'll. Did I post my solutions? That's the question.
Oh, so that was, yeah, no.
I didn't. So,
Okay.
you want to get them to me tonight?
Yeah, I'll do those.
Okay.
Thanks.
Oh, here we go. All right, so now we'll do some counting. We want to know how many positive integers less than 1001 are divisible by 2, 3, or 5. We did one that was kind of similar, where we just said how many are divisible by, I think we just had 2 numbers there. So let's split this up into pieces. We could let A be the set of integers that are divisible by 2. We'll let B be the set of integers that are divisible by 3. And we could let C be the set of integers that are divisible by 5. Positive integers less than 1001 means there's a total of 1,000 integers from 1 to 1,000. Let's figure out the size of each of these sets. We did one really similar. We just sort of review, kind of recall what we did. Oh, not that one. Here. All we needed to do, we know every third integer is divisible by 3, so we took 1,000 divided by 3, then we had to round down, so we applied that floor function. We're going to do that for each of these to find the size of the individual sets here. So the size of A should be 500. The number of integers divisible by 3 should be 333 after we apply the floor function. And this will give us 200. Now, if I just add up all of these numbers, I'm going to way overcount a bunch of values. I'm going to double count, and I'm going to triple count some of these too. I'm going to double count numbers that are divisible by 2 and 3, but not 5. I'm going to double count numbers that are divisible by 3 and 5, but not 2. I'm going to double count integers that are divisible by 2 and 5, but not 3. And I'm going to triple count the integers that are divisible by all 3. So we have a little bit more work to do. We want the size of A union B union C. And so that gives us, we actually just spelled out that result a couple pages ago, like the last class. So we're just going to start out by adding them all together, subtract off the intersections, and then remember we have to add in the intersection of all 3 at the end, because we had basically counted that intersection of all 3 times, but then we also subtracted it 3 times when we subtracted out the individual intersections. So we add it back in to make sure that we count it. So we know the first three numbers. We got to get the others. Let's find the size of A intersect B. So A intersect B means it has to be divisible by 2 and 3, so it's divisible by 6. And that gives us 166. A intersects C. That has to be divisible by 2 and 5. So we'll divide by 10. And B intersects C. Those are the integers divisible by 3 and 5, which means it's divisible by 15. (66). One last thing we need to find is the intersection of all three. So intersect A intersect B intersects C. Divisible by 2, 3, and 5 means divisible by 30. We get 33. One thing I just want to point out, it's a subtlety that we haven't really needed to deal with this type of problem because of the numbers we were given. When we said, like for example, let's look at the B intersects C. We wanted all the numbers divisible by 3 and by 5, so that means it's divisible by 15. And we got that just by multiplying 3 times 5. The reason we could just multiply 3 and 5 together to figure out what we need to divide by is because 3 and 5 are relatively prime. They don't share any common divisors. If this were like, 6 and 15, if I were thinking about what's divisible by 6 and 15, I wouldn't just multiply 6 and 15. I would say I have to find the least common multiple of those two. So just in case that that comes up, if you see a similar problem. I think we're ready to go. Well, these are the things we're going to subtract and then add in that last intersection. So let's see, A and B and C. So we have 500 plus 333 plus 200 minus 166 minus 100 minus 66 plus 33. I get 734. Questions? Okay. All right. Let's move on to permutations. We'll start just with the definition and notation. When you see that little exclamation point, that's the factorial. You might have seen that if you took Calc 2, that comes up in Infinite Series chapter. It's defined recursively. 0 factorial is by definition 1. That's our seed, basically, for the factorial function. And then n factorial is just n times n minus 1 factorial. So 0 factorial is 1. 1 factorial is also 1 because it's 1 times 1. 2 factorial is 2 times 1. You just multiply it by the previous factorial. More intuitively, the way I think of it is it's just the product of all the positive integers from 1 up to n. That intuitive way works for everything except for people get a little bit tripped up with remembering that 0 factorial is equal to 1. Factorials will come in, will be present a lot in this section. A permutation of objects is an arrangement of them, or maybe an arrangement of some subset of those objects. If we permute them, we're basically just sort of scrambling them up. We're not just concerned about what objects we have, but the order in which they appear. So we denote the number of permutations of R objects taken from a set of n objects as P of n comma R. So it's like a function of 2 inputs. And we get that by taking n factorial and dividing it by n minus R factorial. Now, when I compute permutations, a lot of the time, I don't always use that formula. This is really a straightforward application of the multiplication counting principle, but we're selecting without replacement. With permutations and combinations, as we'll see, we're always selecting without replacement. Let's do this example using the technique we already know, and then we'll see why we get the same result using that permutation formula. So if we've got 20 people in an organization, we want to select a president, a vice president, a secretary, and a treasurer. So we're picking 4 people to put in those offices. Now, the order matters, right? We're not just selecting a committee where everybody has equal standing. Like if I'm president, maybe I act differently than if Andrew's president. So the order in which we select matters. So let's say we're making 4 choices. We're making 1 choice for the president, 1 choice for vice president, 1 choice for secretary, 1 choice for treasurer. How many choices? Let's make the choice in sequence. How many choices do we have? How many ways do we have to pick the president? 20. Yeah, there's 20 people in the organization. Now, I'm going to say that 2 people are not going to, or 1 person is not going to serve in 2 different offices, right? So once that 1 person's president, they're not going to be in another role. So how many ways to pick the vice president? 19. And secretary? Yeah, we just keep going down, right? So 20, 19, 18, 17. It's like a standard multiplication counting principle problem. Now, what this theorem tells us, or what this definition tells us, is that if I want to find a permutation of R objects or R permutations on N objects, what I'm doing is finding a permutation of 4 objects chosen from N, or 4 permutations on 20 objects, 20 people. And we would compute P of 20 comma 4. And this would look like 20 factorial over n minus r, that's 20 minus 4 factorial, or 20 factorial over 16 factorial. Now, if you're looking at this and thinking, okay, well, I better figure out what 20 factorial is, and then divide it by 16 factorial, whatever that is, that's the hard way to do it. And, you know, if that's what you're into, you could do it, but I feel like you're not going to have a nice time. There's an easy way to do it. 20 factorial is just all the factors from 20 on down to 1, right? I'm not going to write them all, don't worry, but I'm going to write 20, 19, 18, 17. And then I've got 16 on down to 1. That's 16 factorial. And I'm dividing this by 16 factorial. So I'll just cancel those out. And we get the same product. Larger factorials always contain as a factor that every smaller factorial, right? So I could kind of cut it off. I chose, when I was writing this out, I chose to write it in such a way that I had that 16 factorial. Like I see the 16 factorial appear in the bottom, so that's how I knew I wanted to stop here and just say, okay, the rest of those factors I'm just going to call 16 factorial. Let's do a more interesting one. All right, we're going to figure out how many ways 5 boys and 6 girls can line up for a picture if no 2 girls are to stand next to each other and no 2 boys are to stand next to each other. So there's one more girl than there is boys, right? That means that if they have to alternate, we've got to have it start with a girl and then alternate from there. One, 2, 3, 4, 5, 6. Okay, so that's what it's got to look like. So I know, like, these places here have to be for each of the girls, and then these places here have to be for the boys. That part is fixed. I can't change that. So now the only choices that I have to make, is how to place or how to arrange the 6 girls in those spots. So imagine that the boys are not even there, and I just want to take the 6 girls and arrange them, right? Put them in a line. How many ways could we arrange those 6 girls? I've got 6 spaces and 6 girls. How many ways to pick who goes in the first spot? Say that louder, Andrew.
6.
6, right? And then once I've placed her, how many choices for who goes in the next spot?
5.
Yeah, all the way down to 1, right? Because I'm placing all 6 girls. So the number of ways to place those 6 girls is 6 factorial. The number of ways to place the boys, what should that be?
5 factorial.
5 factorial. There are 5 boys. We just want to put them in some order. So that means now there's 6 factorial ways to place the girls. For each one of those ways to place those girls, I've got 5 factorial ways to place the boys. We're going to use the multiplication counting principle one more time. The total number of ways to line up these kids is 6 factorial times 5 factorial. And let's just see how big that is. $86,400. Fun.
So what about that question makes the permutation instead of the combination?
Oh, well, the combinations would be like, there's only one way. Like a combination, and we'll talk more about this when we get to that part of this section, but combinations are just, suppose I have some set of things and I want to pick some smaller set from them. And that tells us how many different ways I could grab like a set of 4 from 10, right? I'm not going to pick and we're just concerned about which ones we get, not the order in which we get them. With a permutation, the ordering matters. It's an arrangement, it's an ordering, it's a permutation. That's
how many ways we can have.
Yeah, I mean, you'll still see the language, how many ways appear in combinations problems. But the distinction, what makes something permutation versus combination is that the order matters. Here, this is only concerned about ordering, right? I know that I'm taking all 6 girls and all 5 boys, right? If it was a combination, I'd be like, oh, one way, like I've got to grab them all. But this is really just about the arrangement.
From a combination standpoint, it would be more interesting to be asking about how many ways you could arrange them if we had an equal number or something.
Not really. I mean, it would be a combination problem if, and now this feels bad to talk about, but if I was going to leave some of them out. I don't want you're not going to be in the picture. Like, suppose I've got 11 kids, right? And I'm going to be like, you know what? Only 8 of you can be in this picture. And then we want to know, like, how many different ways can we pick those 8 kids?
You're just trying
and
to
we don't care about the order.
The alternating
Mm-hmm.
thing.
Yep. And it's the alternating thing, there's only one way, right? It has to be girl, boy, girl, boy. And then, so like that part was not a choice. If there were an equal number of girls and boys, I'd have to double it because I could also have it boy, girl, right? So I'd get another, same number of permutations there.
Understood.
Yep. All right, now we want to see 10 people at a round table if we're only concerned with whom sits at each person's right or left. So kind of like the relative order, but not the absolute position, if that makes sense. So like, suppose, I'm not going to draw all 10, but like here's 5 seats, right? Suppose I have person A, B, C, D, and E. This would be indistinguishable from this. If I just take that same arrangement and rotate, we're not counting that separately. All we're concerned with here is where are you relative to the other people. It's not that I care who's at this one, it's like who's next to A and who's next to E or whatever.
My graph senses are tingling.
What's that?
My graph senses.
Oh, your graph senses are tingling. Okay. I acknowledge, even if I don't quite understand. All right, so this is interesting because it's really just a relative position that we care about. I'm going to start by making this a bigger problem, like counting too many things, basically. I'm going to intentionally overcount to kind of just get started on this problem. If every seating was different, right? If I was actually concerned with the just absolute position on the table, let's figure out how many seatings there would be. So we've got 10 seats and 10 people to put in those seats. I start with the first seat, say the one at the top. How many ways could I pick the person that sits there? 10, right? And then I move to the next seat, got 9 choices there. I'm placing all 10 of those people into all 10 of the seats. So the number of arrangements there are there would be 10 factorial. Now that's way too big, right? We are double counting and maybe multiply counting lots of seatings. So let's just sort of put that into words. If we have a given seating, let's say one that's like this, only, I've got 10 and not just 5 up there, but I've got the 10 people sitting around the table. And we rotate it. We don't want to count that, right? If we have a given seating and we rotate it once, twice, 3 times, whatever, I don't want to count those as different. Right, which is exactly what we're doing when we say there's 10 factorial ways to seat them. So we're going to account for that, okay? We are going to take that 10 factorial and figure out how many times we have multiply counted the same seating. So how many times is a given seating counted up here? Like we got 10 seats, 10 people. We say if they get up and rotate once, that's counted again here. If they get up and they rotate again, that's counted again. So that same relative positioning is counted how many times up here?
10 total.
10 total, right? Because there's you could sort of fix the person at, you know, the top of the circle and just say how many places could they start at. So each distinct seating for us is counted 10 times. How am I going to account for that?
Then we divide 10 factorial by 10.
Yeah, that's exactly what we're going to do. So each seating is counted 10 times. That means that there are 10 factorial divided by 10, which we could reduce. That's 9 factorial seatings. And if we find that value, wow, 362,880. How's that?
I'm curious to know how it would be different if the question were worded differently in the second half. Like, what if we're concerned with who sits at the person's right and further right, and left and further left?
I mean,
Would it be the same?
I think it's the same because you're still talking about positions relative to each other, right?
Okay.
Yeah.
All right.
Okay. Let's try another. More books on a shelf. We've got a collection of 15 distinct math books, so they're not just 15 of the same book. Same for physics, 12 physics books, 16 computer science books. That gives us a total of 43 books altogether, and we want to put them on a shelf. We want to figure out how many ways we can do this if there are no restrictions. Like any way I choose to throw all of these books on the shelf is fine. What should we get?
Is it gonna be 15 factorial times 12 factorial times 16 factorial?
Not this time.
Okay.
That would actually include some restrictions. So if I'm talking about no restrictions, I imagine that I don't.
It's 43 factorial.
Yes. Yep.
Okay.
Right, because like which subject is which doesn't matter to me then, right?
Okay.
So this would be 43 factorial. Now, if we want to group the books on the same subject matter together, that's when we're going to have 15 factorial, 12 factorial, 16 factorial. Now, we're not quite done this part, right? So this is putting the math books together, the physics books together, the computer science books together. But look what I did. When I wrote it out that way, I said I'm putting the math books first, and then I'm putting the physics books next, and then I'm putting the computer science books. But I don't necessarily, the subject matters don't have to be in that order, right? It would be perfectly fine if I put the physics books first. So what I need to do...
You gotta tack another 3 factorial on.
Yeah, 3 factorial. That's how many ways I could arrange the 3 subject matters. Now, one slightly different question in C versus B. All books on the same subject are placed next to each other, so same deal there. And then the computer science and the math books can't be next to each other for reasons. So again, we could start the same way, right? We've got 15 factorial, 12 factorial, 16 factorial. Again, when I write it out that way, what I'm saying is I'm putting the math and then the physics and then the computer science. But that's not the only way I could arrange the subject matters. How many different ways do I have to arrange the subject matters now?
2 factorial.
Yeah, yep, because we know basically that physics has to be in the middle, right? And then it's like, where does math go? Where does the computer science go? So it has to be math, physics, computer science, or computer science, physics, math. Note that the actual books that we have on our shelf don't change. This is about arrangements. This is about an ordering of objects, which is what makes it a permutation problem. Questions before we talk about combinations? Okay. All right. If we want to pick our objects from a set of n objects, but we don't care the order in which they come, all we care about is which ones we end up with, what we get, and not the ordering, that's a combination. So the number of R combinations of n objects. Some textbooks, you might see this notation, the C of nr, similar to the permutation notation, but far and away, this notation is much more common, and it's the one I'm going to use. So we put the parentheses, we put n over r. Note that it's not a fraction. There's no fraction bar. And when we say this, it's really common to say n choose r. That's the number of ways that we can pick r objects from a set of n. The formula is really similar to the permutation formula. The difference is the presence of this factor of r factorial in the bottom. And the reason that that r factorial is there in the bottom is because in a permutation, right, if I've selected r objects, I count each of those, and the order matters, so each of the same set of r objects in a permutation, I count r factorial times, because I care about the order. So you could think of it as starting with that permutation formula and then saying, well, once I've picked my r objects, I'm going to divide out, because I don't want to like multiply count those arrangements of the same objects. The first thing we'll do is show that n choose r is equal to n choose n minus r. This is actually pretty easy to show using the formula, and then we'll kind of talk about why it makes sense that those should be equal. So n choose n minus r, I'll start there, and I'm going to use the formula in the definition. So I've got n factorial on top. On the bottom, I should have n minus r, right? I subtract the bottom number from the top, factorial, and then n minus r factorial. N minus r, what does that simplify to?
Plus r.
Yeah, it's a positive r, so I've got r factorial n minus r factorial, and wouldn't you know that's precisely the formula for n choose r. So I'm going to use an example to show you intuitively why this definitely should be true. So let's compare 20 choose 6 versus 20 choose 14. Right, so in this case r is 6, so 20 minus r is 14. The reason that these are equal is that picking up here, right, in the first combination, we're considering that we've got like a bag of objects or whatever, 20 objects. I want to reach in, I want to grab 6. And we want to know how many ways can I grab those 6 items. So we're picking the 6 items we want. But look, once I pick those 6 items that I want, what's left? How many items are left in the bag? No. I've grabbed the 6 from the bag.
Okay, 14.
Yeah, 14 are left in the bag. In fact, choosing which items I'm going to take out of the bag is equivalent to choosing which items I'm leaving, right? When you have n choose r, in this case 20 choose 6, what I'm doing is I'm partitioning those 20 objects from which ones I'm going to take, which ones I'm going to leave. So picking the 6 items we want is equivalent to picking the 14 items that we don't want. We know that if a set has 10 elements, then there are 2 to the 10th subsets, right? We know how to find how many subsets a set will have. So of those 1,024 subsets that it does have, suppose we want to know how many of those subsets have 3 elements. What we want to find is, of those 10 elements, how many ways can I just pick 3? We want to compute 10 choose 3. Using the formula, 10 factorial over 7 factorial, 3 factorial. I don't know if I necessarily need a calculator for this. 10 factorial contains 7 factorial as a factor. And 10, 9, 8, 7 factorial. Those will cancel. 3 factorial, you know what, I'm going to go ahead and write that as 3 times 2. And then I can do some reducing. 3 goes into 9 3 times, 2 goes into 10 5 times. So we're left with 5 times 3 times 8, which is, what's 15 times 8? 120. There are 120 3-element subsets. How many 7-element subsets are there?
Rachel,
Yeah.
where'd you get the 2 in the denominator there?
Because it was 3 factorial.
Oh, which is 6.
Yep.
Gotcha. Okay, thank
Yep.
you.
How many 7-element subsets are there?
$120.
120. Right? Picking the 10 choose 3 has got to be equal to 10 choose 7. Okay. Questions so far? All right. How many ways can a committee of 6 men and 8 women be selected from a group of 12 men and 20 women? So note that this is just a committee. I'm not choosing like officers. Supposedly, if you're sitting on a committee, everybody kind of has equal standing. So I don't care the order in which I select people. I just care who ends up on the committee. Now there's a restriction, right? I mean, I know I've got a total of 32 people and I want to pick 14 of them, but there's restrictions. I want to make sure that I have 6 men and 8 women on this committee, and I know I'm choosing from 12 men and 20 women. So what we'll do is just take care of the individual restrictions first. Let's figure out how many ways can we pick the men. Well, I want 6 men, and they have to come from the 12 men that are there, that are available. So that is 12, choose 6. The number of ways to pick the women, what should that be?
20 choose 8.
Yeah, 20, choose 8. I want to choose 8 people that come from the 20 women in the group. Now, computing the combinations by hand is actually kind of fun and a little bit enjoyable, and I would be lying if I said it wasn't, kind of soothing and therapeutic. But your calculator can also compute combinations for you, so I'm just going to show you where that is in the menu. It's in the same menu as like the factorial is. So if I want to compute 12, choose 6. What I do is I hit the first number, 12. Now I go to the math menu and over to probability. And then the third option is NCR. That's N choose R. And then I put the other value, which was 6. And that gives us 924. Similarly, 20, choose 8 is 125,970. So we've figured out individually how to pick, which women end up on the committee, which men end up on the committee. But we haven't figured out how many ways we can just form the committee wholesale, right? Like, for each of those 924 ways to pick the men, there are 125,970 ways to pick the women. So how many ways to pick the committee total?
Apply the multiplication calculus.
Yeah, we're just going to multiply them together.
I guess for each is kind of what we're looking for to apply that, right?
It's almost like, think of it as a as a counting tree with like a ridiculous number of branches. Yeah.
I can visualize it.
Yeah. Unpleasant to visualize, really. Oh boy. 116,396,280. Questions so far? If there were no restrictions on this committee, I didn't care like how many men and how many women. If it ended up all women, that'd be fine. Or if it ended up all men, like wouldn't care. How would we compute the number of ways that we could pick the committee in that case?
Would we start by doing 12 choose 12 and then 20 choose 20?
Oh, well, 12 choose 12 and 20 choose 20, they're both going to be 1, right? If 12 choose 12 is like, if I have a set of 12 and I want to pick all 12, how many ways can I do it? And there's only one way, you got to take them all.
12 factorial times 20 factorial.
No, that would be...
Sorry, no,
that-
it's 32 factorial.
Well, no, it's not 32. So 32 factorial would be, let's take all these 32 people and figure out how many different ways we could line them up. I still want to make a committee, right? Right? So, Andrew?
Is it just 14 factorial because you have...
It's not 14 factorial. 14 factorial is if I have 14 people, how many different ways could I line them up? But I want to pick 14 people from the 32 people that we have. It would be...
Oh, it's 32 choose 14.
Yeah. Now, I'm not going to compute that. It'll be something that's ridiculously large. But what if you throw it in the calculator, you should find that it is just so much larger than this, right? Restrictions, when you consider restrictions, that should make your results smaller, right? So that's one thing to kind of keep in mind. That's one reason why when we approach counting problems, sometimes you might maybe add a different restriction or like try to consider a subset, like make the problem a little smaller. Sometimes can help you get started on a counting problem. Like here, we said, you know what, I'm going to look at just this small problem here, the number of ways to pick the 6 men. I'm going to take care of that particular restriction first. Sometimes, so that approach worked here. Sometimes I use an approach to make a problem bigger, like where I know I'm like over counting, but it's something that I can account for, like when we were working with the ways to arrange people seated in that round table. Let's do another one. This one's pretty short. How many distinct 5-card hands can be dealt from a standard deck of 52 cards?
52 shoes.
Mm-hmm. Yep. And we could do this up by hand, but and that's fun and all. You'll get 2,598,960. It's why casinos make money, and then now consider that they work on like a 5-deck shoe or something, right? Like. Okay, now let's do another one. How many ways? What did you?
Oh, no, I don't know.
No? Okay.
Okay.
Oh. How many ways are there for a 5-card hand to be a full house? Right. So these are just the total number of cards, where maybe nothing special about them. Right. Maybe it's a crappy hand. Maybe it's a great hand. I don't know. But those are all. That's the possibilities. Let's figure out how many ways there are to get a full house. So a full house is where you get 3 cards of one rank and 2 cards of another rank. For example, like 3 kings and 2 sevens or something. That's a full house. So that's important to know, is that we have a 3 of a kind and a pair. What's helpful to understand about this is that full house accounts for all 5 cards in your hand. That's good, all right? Like if I were just thinking about how many ways to get 2 pair, those 2 pair that I want would only account for 4 of the 5 cards, and then we have to kind of consider that 5th card separately. But this accounts for all 5 cards. We're going to handle these restrictions separately. And I think it'll be helpful to first make it an even smaller problem. Let's look at a particular full house of 3 kings and 2 sevens. So let's figure out how many ways to get the kings. So I want 3 kings. Overall, what that means is I'm taking 3 cards. I'm picking 3 cards, and I need them to come from the 4 kings that are in the deck. So the number of ways I can get 3 kings is 4, choose 3. What should 4 choose 3 be equal to? 4. Yeah, because 4 choose 3 is the same as 4 choose 1, right? So if I've got 4 cards and I just want to pick 1, there's obviously 4 ways I could do that, right? Pick one of those 4 cards. What about the number of ways to get the sevens, to get those 2 sevens? What combination are we going to use there?
Or choose 2.
Mm-hmm. And if you do that out, you'll find that you get 6. So now, the number of ways to get this particular kind of full house, the 3 kings and 2 sevens, we're just going to apply the multiplication counting rule. It's 4 times 6, or 24. 24 ways to get that particular kind of full house. But that's obviously smaller than what I'm going after, right? Because I just want any old full house. I also want to count, you know, 2 2s and 3 queens or whatever. Like, so I know the final answer will be bigger. And what we need to do now is account for the number of ways we could choose those 2 ranks. So let's do that. Now, there's a little bit of a subtlety here. How many ranks are there? There are 13, right? From ace up through king. And I want to pick 2 of them. Now, it might seem at first that we just say, oh, 13, choose 2. But that would be us saying that the order doesn't matter. And I would like to consider the possibility that getting 3 kings and 2 sevens is different than getting 3 sevens and 2 kings, right? So the order in which we pick the ranks in this case matters. The order in which we pick the ranks, if I were doing like trying to figure out how many ways to get 2 pair, wouldn't matter, right? Because 2 kings and 2 sevens, same, doesn't matter. Here it does matter. So I don't want to use a combination here. I just want to use the multiplication counting principle and get 13 times 12, which is, by the way, the same thing you get if you find the permutation of 13 and 2. And that gives us, well, let's see.
The reason it's 12 is because you can't get 5 kings.
Yeah, we can't get 5 kings, yep. And also, like, if it's a proper, even if I could, let's imagine we had some weird deck that did have 5 of each thing. If it's a proper full house, they should be different ranks. 5 of a kind would probably be a different hand.
Right.
Yep. So the number of ways to get a full house. Is 24 times 13 times 12, which is 3,744. You know, that might seem like kind of a big number. It is a little bit, I guess, but it's really, really small when you consider the fact that there's over 2.5 million ways to just get any old 5-card hand.
Refreshment. I mean, usually when I play poker, I try to go for a full house, but maybe I'll try something else.
Oh, okay. So I'm going to save this last page for next time because I'm sure it'll take us more than 5 minutes to get through it. So between now and I guess if you have questions as you're finishing up the test, text or email your questions. I'll be in and out of responsiveness with a couple of appointments I have this evening, but I'll be checking my messages. Other than that, enjoy the rest of your day. If you find yourself on the Williston campus tomorrow, we're celebrating Pie Day in the library at noon, so there'll be lots of pie, and you can come by. Enjoy the rest of your day, and I'll see you all again on Monday.